Hi, everyone. Thanks for attending this talk, Detecting Road Conditions from Space Using PyTorch, Public Data, and Free Satellite Imagery. My name is Cynthia Ukawu, and I'm a mathematician and back-end software engineer with about 5 years of experience. I've worked across data analytics, geospatial analysis, and building infrastructure for machine learning models. I've worked with mobility and location-based data at scale. I've done things like enriching raw GPS traces, performing geospatial joins, and also building out pipelines to support downstream modeling and analysis. I've worked with data scientists who also do geospatial analysis with mobility data to help them with driver behavior or predicting crashes. So I have a lot of experience with geospatial related stuff. These days I focus on processing satellite and aerial imagery and designing scalable systems to prepare, store, and run these models. I am passionate about using open data and open source tools to build meaningful projects. And this talk is about sharing that process with you so you can also create your own trained model and use it for civic projects or other fun computer vision projects. So the problem that I was dealing with is infrastructure. Many of you probably have experienced a pothole or experienced the trouble with hitting a pothole. Maybe you spilled your drink or you braced yourself. I know when I run into one and I can't swerve out of it, I brace myself for impact. But poor infrastructure in America is a multi-billion-dollar problem. So hitting a pothole could cause your car to need an alignment afterwards. And if you were to multiply this problem by thousands of drivers every day across every city in the country, we run into this huge issue. So bad road conditions aren't just an inconvenience, they're a multi-billion-dollar problem. And according to a March 2025 report by TRIP, a National Transportation Research Group, poor or mediocre roads cost Maryland drivers alone an extra $12 billion annually in vehicle repairs, lost time, and wasted fuel. Also, according to the American Society of Civil Engineers' latest infrastructure report card, 39% of major roads in the US are in poor or mediocre condition, costing the average driver over $1,400 per year in vehicle operating costs and lost time. I do know for the state of Virginia, if you do hit a pothole and you get damage, you can file a claim so check with your state. That's some legal stuff. I'm not a lawyer though. Okay, so on to the next one. So for city governments, maintaining roads is equally expensive and slow. Most rely on manual inspection. They hire teams to physically drive around and rate pavement conditions, and sometimes they use Excel sheets or clipboards, but the process is very slow and labor intensive. It's reactive and often only catches the worst issues after damage has already been done. However, what if we could automate part of this process or at least streamline it? Instead of waiting for roads to fall apart, we could predict their conditions directly from the sky using satellite imagery and machine learning. So this project was inspired by a research paper published by the GeoLab team at William & Mary titled Predicting Road Quality Using High-Resolution Satellite Imagery, a Transfer Learning Approach, and this was featured on PLOS1. And this study demonstrated the feasibility of applying deep learning techniques to classify road quality. So for my project, I had two goals in mind. The first one was to fine-tune a ResNet 50 model on satellite imagery provided by the GeoLab team. So I used the same images that they used in their research paper, or at least a subset of it. And then my second goal was to use that model to classify road segments from VDOT's dataset. And VDOT is short for Virginia Department of Transportation. So it was almost like a supervised sort of learning where I would train this ResNet model and see how well it does using actual classifications from VDOT. So like I said before, this pre-trained ResNet 50 model was the backbone for this project. And ResNet 50 is a convolutional neural network, or CNN for short, with 50 layers. And CNNs are really great for visual tasks like image classification or image segmentation. And I used the PyTorch implementation of ResNet 50. And ImageNet is a large, publicly available image data set that's widely used to train and evaluate computer vision models. It has over 14 million labeled images. So with a pre-trained model on ImageNet, we can fine-tune it to specific tasks. And in this case, our specific task is to classify road conditions. And that's the beauty of transfer learning. You don't have to start from scratch. You can use something and build on top of it. So this is a screenshot of the landing page for the data that was used. So it's split up into two. There's the directory for the images. It's a little over 4 gigabytes. And then there's also the file that has all the labels. For this project, I used Google Colab because it provided access to TPUs, which are really helpful for speeding up deep learning tasks like image classification. I originally tried to use the full data set from the research paper, which has over 50,000 different satellite images, and these images were hosted on Google Drive. However, when I tried to load all the files, I kept running into input-output errors, and this is probably due to how many files were being accessed at once. So I was just trying to read in the file names, and it was giving me issues. So instead of that approach, I decided to create a smaller, balanced sample of the data. And what do I mean by balanced? So for each category, there needs to be about the same number of images. We want a stratified or balanced sample because if you don't maintain class balance, your model will mostly see and learn from the dominant class. It will get lazy and biased towards that dominant class. And your model could achieve high overall accuracy just by guessing the majority class, even if it sucks at detecting minority class. And the focus of this project was to detect poor road conditions. So we don't want that sort of bias. So an example of a bad imbalance is, suppose 90% of the training data is good roads. The model can predict good 90% of the time and look accurate, but it would miss poor roads. So maintaining that balance forces the model to pay attention equally to poor roads, fair roads, and good roads. It learns meaningful features of what a bad road looks like versus what a good road looks like. And for this slide, this top part here is a snippet of the labels CSV file. So it has 3 different columns: the ID, the CQV, and the int label. And then at the bottom here, I don't know if you can see my mouse. Oh, yes, you can. So at the bottom here, these are just sample images, a screenshot of what I took. So this first ID here, 384605, matches this image at the very far right. And the int label gives you the category. So 0 means poor, 1 is fair, and 2 is good. And then CQV is a sensor measurement, which was used to create the int label column. And the math behind how the CQV was created can be found in that paper that I mentioned earlier. So one thing about this data set, even though there was over 50,000 different satellite images, there were only 712 images that were labeled as poor. So I had to match for the other 2 classes as well. And that left me with just a little over 2,000 images, so 2,136 images in total to work with. And that is not a lot of data when you're trying to train a deep learning model. And this can lead to overfitting. In fact, that's what I experienced. So after 4 epochs, and an epoch is a loop over the training images. So after 4 epochs of training, the model started to memorize the training data instead of generalizing it to new data. And I could tell because the training accuracy kept going up, but the validation accuracy flattened at around 65%. and the validation loss stopped improving. So the divergence between training and validation metrics is a classic sign of overfitting. The model was memorizing rather than learning, unfortunately. So even though I had a balanced data set, I still had to worry about overfitting due to the small number of images that I was working with. So this slide is a screenshot of one of the tools that I used, which is geojson.io. So high-resolution satellite images are typically costly, and they require paid subscription. So I relied on freely available sources like geojson.io, which is provided by Mapbox, Google Earth, and also Google Maps. And even though these were great starting points, I did run into issues where the street name would be on the actual road, and I couldn't get rid of it. So taking snapshots or screenshots of the road was kind of difficult. And also there were places where there was lower resolution because it was in rural areas. So that could potentially confuse the model and compromise prediction accuracy. And in this screenshot here, I am looking at this particular road segment. I used GeoPandas to import the data from VDOT, and I'll show you that. So this screenshot, the top is the data set that I used, which is the VDOT pavement conditions 2024. And this snapshot here is me reading in that data into GeoPandas and then setting the coordinate reference system. So for those who aren't familiar, GeoPandas is a, I wouldn't call it a wrapper, but it's like pandas, but with geospatial data. So it has that lat-long attribute. So I use GeoPandas to store and analyze the data. And when you're working with geospatial data, you often deal with something called a CRS, which is short for Coordinate Reference System. And this tells the computer how to map points on the Earth's surface. So this function here, .2CRS, ESPG, EPSG 4326 is that function there converts your geospatial data into a different coordinate reference system. And 4326 is the standard that's used for a lot of different web maps like Google Maps. So if your shapefile or geo data frame was originally in a different projection, like meters, you'd need to convert it to degrees or lat long so that it can be compatible for tools like Google Maps or other web maps. So if your geospatial data set was in meters before, that's probably because you were doing something that deals with finding distance between 2 points, and that's when you would use a projected coordinate reference system. So another issue that I did run into, or another constraint, was that the test data that I got from VDOT had a lot of detail. And what I mean by that is that there were actually 5 different categories. There was excellent, good, fair, and poor, and very poor. But the model that I used only had 3 different categories, so good, fair, and poor. And in order to make things work, I had to combine these original labels. So excellent and good were combined to form good, and then very poor and poor were combined to form poor, and then fair was left as is. And collapsing the categories likely meant losing important distinctions. For example, a road that's labeled as excellent is different from labeled as good, but the model treats them as the same. So while the training ran, some of the original nuance of the data was lost. So yeah, between the limited data set size and the need to reduce the categories down to 3, this model was already at a disadvantage. It was trying to learn subtle visual cues from limited and overly simplified data. So that made meaningful generalization really difficult. So here is oh wait, I did want to go back to that. So here for this road segment, I had the data frame, and I was just looking at random route IDs. And so this route ID, I just converted it into a GeoJSON file and then uploaded it to this website in order to get this image here. Okay, So here is route 74NB. I'm only going to use the last four characters of the actual ID when I'm calling out these different image segments. But this is what I took on Google Maps. It's a standard screenshot, nothing fancy, but this is actually what I fed into that trained model. And this is a code snippet of what I used to get that prediction. So let's start from the top. Val transforms defines a set of transformations to apply to each image before it's passed into the model for validation. And the goal is to make sure that the input images are in the same format, size, and distribution that the model was trained on. And after defining the transformations, we open the image and convert it to RGB because the model expects 3 color channels. Then we apply those transformations we defined earlier. And then finally, we use unsqueeze to add a batch dimension. So for deep learning models in PyTorch, it expects inputs to be batched even if there's only one image. And then for the width clause, we're saying don't track gradients since we're not training, we're just predicting. And then we pass the image through the model to get the output, which is a set of scores. You can think of it almost like a list. And then you run this argmax to find the index of the highest score. And the index of the highest score is the predicted class. And then .item will convert that PyTorch sensor into a regular Python number. And then lastly, we print out the prediction. So here, the model predicted this road segment as being good, and VDOT rated it as excellent. So the model is on the right track here. And for these next few road segments, I'd like you to assess what you think this road segment would be, whether it's good, fair, or poor. And then I'll show what the model got, and then I'll also show what VDOT rated it as. So you can write it down or think about it or say it out loud. It really doesn't matter. But here's route 76EB. Okay, so the model predicted this as fair, but VDOT rated it as very poor. So here is route 22NB. The model predicted it as fair, while VDOT rated it as very poor. And here's 96NB. And again, I took screenshots from Google Maps. I wasn't working with much. But the model predicted this as fair, and VDOT rated this as very poor. Here's route 30NB. So again, the model predicted this as fair, and VDOT gave this a rating of very poor. 21EB. So this was also fair, but VDOT also gave this a rating of fair. And I have 2 more road segments. So here's the next one, OANB. So this got a rating of fair, and VDOT rated this as good. And then this last one, which is 58EB. What would you rate this road? Yeah. So the model rated this as fair, and you and I can both see that this is a very excellent road. And I wanted to show you this road, because when I saw that the model gave this rating of fair, I was like, what? This is insane. But as you can see, this road it looks like it was repaved. It's just a really nice looking road. So I was, taken aback when I saw that rating of fair. But I'll go into perhaps why it was relying so heavily on that category fair. Okay, so here is a normalized confusion matrix and a classification report. And a confusion matrix shows how often the model's predictions match the true labels and how often they confuse one class or one label for another. So the top is the, so this top part here is the normalized confusion matrix. And we're looking at how well the model predicted the 3 road conditions, so poor, fair, and good. Each row represents the category, and then each column represents the model's prediction. And the numbers are normalized, so we see percentages rather than raw counts. So at the top, we have poor. So 70% of poor roads were correctly predicted as poor, which is really good, while 23% were misclassified as fair, and 7% were incorrectly classified as good. And then for the middle row for fair, 62% of fair roads were correctly identified, and 31 were misclassified as good. And a small portion, only 6%, were predicted as poor. And this is where the model really struggled. So it was confusing fair roads and good roads, interchanging those two. And it might have been due to the reduced number of categories, because it was originally 5, and I had to reduce it down to 3 to match with the model. And then at the bottom row, we have good. So 64% of good rows were correctly identified or predicted, and then 29% were mistaken for fair, and then 7% were mislabeled as poor. So the model, correctly predicted good roads 64% of the time, but it still confused it with fair roads about 29% of the time. Again, showing some ambiguity between these adjacent categories. And then for the classification report, we have precision, which tells us how often the model is correct when it predicts a class. And recall measures how well the model identifies all the true instances of the class. And then F1 is like the balance between those two scores. So the model is confident about poor roads. So it has a high precision and a pretty solid recall. But for fair, the performance drops down. And if you look at the F1 score, it's like around 0.58, which reflects how messy that middle class is. And the overall accuracy for this model is 65.7%. So the model gets about 2 out of 3 predictions right. And this confusion matrix that I mentioned above is a great illustration of real-world fuzziness. The model does well on extremes, like identifying poor roads, but it struggles with in-between classes like fair roads. But given the fact that I was working with less than 3,000 images, and I had to reduce the categories from 5 to 3, and I was also using crappy images that I snapshotted from Google Maps, I'm actually quite surprised that the accuracy is 2 out of 3. That's pretty good for a side project. So what are some of these takeaways? The model showed that it can learn from satellite imagery and classify road conditions with decent accuracy, so around 66%. And that's not bad considering all the nonsense that kind of went into it. The biggest challenge was distinguishing between fair versus good, but the original problem that I was trying to tackle was identifying poor roads, which this model can do. So yeah, the main goal of the project wasn't to build a perfect model. It was to show that you can use open source tools like PyTorch and public data to build a meaningful computer vision project from scratch. Yeah, there were limitations, like the low resolution images, a small data set, and simplified class labels, but that's the point. Real world data science is really messy, and perfection usually requires money. So, money provides better images, more data, and more compute power. And even with all these limitations, the model still reached validation accuracy around 66%. So this just shows that with open source tools and publicly available data, you can build real working computer vision models. So no, it's not perfect, but it works, and that's the core message. Like, you don't need an enterprise resources to start building. You just need curiosity, code, and the willingness to work with what you've got. So that's pretty much it. I wished I could have gotten further into like the actual step-by-step on how I use the tools to get to my final result, like working with GeoPandas and using Mapbox and all that, but that couldn't be done in like 30 minutes. So I have my newsletter, and I'm going to eventually post like a walkthrough of that step, and you can also check out my LinkedIn. And that's pretty much it. Thank you.
So we do have a few minutes more. I think maybe we can squeeze in a couple of questions if anyone has one. Okay.
Hi. So I had one question. Do you have annotated data, pre-annotated data, or you annotated your images by yourself? Did you have like pre-annotated data, or you annotated the data by yourself?
Which data, VDOT data or the images that I use to train the model? So the VDOT data is already classified, and this is found on the Virginia State Department of Transportation. You can download that image. I didn't do that classification. So pavement engineers and the government did that. As for the satellite images, they were also classified by the GeoLab team that I mentioned earlier. They're the ones that produce the images and also created the scores from 0 to 2. Hopefully that answered your question.
Hi. So I was curious, because you have a limited data set, could generating like artifacts in the image or some sort of synthetic generation help improve that model? Like generating artifacts into the image itself.
Oh, fake potholes. I'm not sure if that would improve the model. I feel like it would cause more confusion or not make the model that well. I did mention earlier that when I was taking the screenshots, there was route names and route codes on the actual roads, which would impact the model identifying stuff. And also, I'm not that well versed in Photoshop, so I don't know how to like put potholes on the snippets that I took. So yeah.
Whoa, looks like we have a bunch more questions.
Can you talk about any tuning that you had to do to the model or adjustment of weights? Yeah.
I have to open up my Google Lab to see all the code that I've done. If you do want to see my code and the extent of that, I will have that uploaded pretty soon. It's just that I'm on a different user. Like on my computer, this is for Pyohio and not my personal one that has all the code on it, so I can't really walk through all the tuning that I've done, unfortunately. Yeah.
Fortunately, I won't be taking extra questions, but I believe once she's done cool enough, you can find her in the hallway and then, yeah. But I actually also wanted to chip in my own question. It's more of like, it's more like a twofer. The data set you're using, is it only, so what happens if you, what happens to the model if you're using, say, 9 picks? And then what is also the effect on the model when you have like road markings? Because I saw a road we all could tell was an excellent road, but it didn't have any markings and it was way off, so I don't know if you can speak to that.
By markings, do you mean the road name or?
No, like how to split the oncoming traffic and those lines on the road.
Oh, that was a subdivision road. So I don't think roads and neighborhoods actually have like those line markings. And then your first question was? Oh, yes. So that's another thing. To improve the model, definitely doing some sort of like, what's the word that I'm looking for? Just doing work on the image itself, like bringing up the brightness or something like that, because I did run into that issue where the screenshots that I took were kind of dark because of the shading from the trees, and I'm pretty sure that infected or had an impact on how the model was predicting as well, and probably why it was, you know, leaning towards fair roads. But yeah, what was your first question again? Okay, so yeah, the lines on the road is, it's in a subdivision or a neighborhood, so it doesn't have lines on the road. Oh, it behaves fine. So my very first screenshot has those markers. Is this what you mean? Yeah. So it was able to identify this as a good road. It gave this a rating of 2, and VDOT gave this an excellent. Yeah.
Another round of applause for our first speaker.